All right, we're going to now look at section 7, 8, and 9. Section 7 deals with nuclear power and fission in particular. Fission is where you have heavily nuclides that are struck by slow-moving neutrons. So this picture right here up in the upper right, that is fission. Okay, the fast-moving ones would bounce off and do not actually do fission. The slow-moving ones are absorbed by the uranium. The uranium then splits spontaneously. It splits into two things and then 3 neutrons. Okay, and these just happen spontaneously again. You have what are called chain reactions, which is kind of the picture right below it. Okay, I let 1 neutron out, okay, and 1 neutron will cause 1 fission. Then I have 2 neutrons. Well, 2 neutrons create 2 additional fissions. Then 4 create 4 more fissions. So you end up with a chain reaction where 1 leads to 1 leads to 1 leads to 1. Okay. Now you must have a minimum mass to have fission, otherwise your neutrons can escape and kind of leave before they actually get absorbed. And so we call that a critical mass. So a subcritical mass here is the smaller one where the chain reaction actually stops before it can actually get going. The other side is what we call a supercritical mass, where you have too much and it accelerates and goes too quickly, and then you can actually have a nuclear explosion. You want the middle. You want what we call a critical mass here, the minimum mass that something has to have to be able to absorb that neutron. And then, like I said, a much larger mass will create a supercritical mass and lead to a nuclear explosion where the chain reaction goes too quickly that it just gets out of hand. Now, atomic bombs are where you have 2 subcritical masses of uranium-235 that then are slammed together. They cause this chain reaction that's really, really rapid, uncontrollable. So now we've got a supercritical mass. Too much is going on. The chain reactions are going too fast, and we have the same energy as 20,000 tons of TNT. So you have these uncontrollable reactions that just go until they really can't go anymore, and they go so quickly that it causes an explosion. And that is fission. Section 8 here with fission is dealing with a nuclear reactor. Okay, nuclear reactors are energy generated by fission. You have a few parts to keep these reactions kind of under control, right? Because we still have this uranium-235 reactor core, and that's the picture that you have here. We have what we call control rods that keep the mixture from overheating and absorb the neutrons to kind of keep the reaction under control. So we have these rods that kind of go into this to kind of keep that mixture from becoming a supercritical mass and becoming an atomic bomb. Okay, you also have cooling fluid that circulates to kind of get rid of the heat that this reaction generates, and that's the part right here with the water. Okay, you also have a coolant or a moderator, which is kind of like the control rods that slow these neutrons down and capture them, and they also then slow the reaction down, so we don't have too many neutrons kind of going every which way. But a nuclear reactor actually makes steam. Okay, the nuclear reaction creates this heat. The heat then heats the water. The steam then powers a generator, okay? And then the generator then is what creates the electricity, or that moves the generator to have the electricity be created. So you're not actually using the nuclear power strictly that generates the reaction or generates the energy. It's more of it kind of heats up the water that then uses this kind of a steam power and electrical generators to create our electrical energy from that. Okay, nuclear power in terms of fusion. Okay, fusion now is where you have light nuclei that are fused together into heavier ones. The energy produced by the sun is done with fusion. Okay, fusion products are nice because they're not radioactive, where fission products are really radioactive, and you have all kinds of nuclear waste that just doesn't go anywhere. These are light isotopes that have high abundance, but also have really high energies. So you have to have these huge temperatures that are needed to overcome these nuclei that I'm trying to fuse together. Because nuclei, a positive and a positive, don't really want to be together. So I have to have all this temperature to get them to move so fast that they don't realize that they're together, and that is fusion. And these are thermonuclear reactions, and the lowest one needs 40 million degrees Kelvin. So we need a lot of heat. We don't have anything that can actually hold that heat or generate that amount of heat. The only way they've kind of come across to get that kind of heat is to use an atomic bomb to initiate the reaction And that's just not an acceptable way to generate power. You can't use atomic bombs every time you want to generate some electricity. So that's not really working. And like I said, there's no known structure that's available to withstand these huge temperatures. Now they have some things called the tokamak, which is a structure that holds or has a really high magnetic field, and that gets a temperature close to that, but they're still not there yet, which is why we do not use fusion yet. Still waiting on that one. The last thing deals with radiation in the environment and dealing with your body tissue. Okay, no matter what absorbs the radiation, okay, it can either cause ionization or excite the matter, and that can be a problem if we have some ionization. You have alpha particles at the top, which don't even penetrate the skin. You have beta particles that part way, and gamma particles go all the way through your organs, which is why gamma radiation are so terrible, because they can, if they're ionized, or if they ionize some of the stuff in your system, that's where you get the problems. It's not the actual radiation, it's the ionizing radiation. Or you have an electron that's removed, and now I have an ion that's causing problems inside all of my organs, my body tissue. There are a couple of ways to measure radiations. There are RADs, which are the radiation absorbed dosage. You have REMs, which are retinogeniums for man. And you have grays, which are certain joules per energy per kilogram of tissue. So there are others, but RADs and probably REMs are probably the most common, but you also have grays as well.